All right, so we had a homework assignment, right? How'd that go? Huh?
It went.
Not bad? Yeah. All right, so we went okay? All right, good. Okay, so we've already talked about threads kind of at a high level. Let's talk about them at a relatively low level, but I'm going to probably zip through this chapter fairly quickly. So I guess just hold on for the ride. So I'll zip through it, but then I'll just give you a quiz on some random part about this that probably I didn't cover very well. Right, that's good. Should be up on...
No, I downloaded all of them earlier.
You shouldn't have to download, it's the link.
I like editing my own.
Oh, I gotcha. I didn't know it let you download them. It's an iCloud thing?
No, I just searched it.
No, it's Keynote. You can download from Keynote too.
People edit all your stuff too.
Yeah.
Different formats you can download it.
All right, but so I share it with iCloud though.
Yeah, so you can download it from.
Oh, you mean you search for this from the book? You got the slide set from the. I get it. You're not from my source. From I get it.
No, you can still get it from your source.
So iCloud allows you to download the Keynote. I get it. Okay, so let's talk about. Let's skip through this. So basically, what this chapter is about is threading libraries. How threads are implemented differently inside of different, we could say operating systems, but they're talking about Java threads versus threads in Windows versus what are called P threads, which are kind of our Unix threads, and just how those guys are how the implementations are different and what are the connotations of that. Okay. Already really talked about this, so forget about that. We know what threads are. Benefits of threads, we know what that is, right? Non-blocking, blah, blah, blah. Okay, so multi-core programming, this is where things start becoming a little bit interesting with threads. So up to this point, we've talked about threads being owned by the process that created it, right? And that process is being scheduled by our CPU scheduler. All right, now, ideally, if we have a quad-core computer, so a computer with four individual processors that can do 4 things at once, not all jobs are divisible, right? So we might have 20 programs running our computer, but we might not be able to do 4 things at once all the time. Make sense? Now, would you say that modernly, based on what we've discussed, it's probably more common for programs to spawn threads or more common for programs to fork child processes, which is probably more common today? Really? Based on what? We've said that's the old way of doing things, right? Yeah, threads would be the new way of doing things, right? Threads they're safer. Right? But we can't take over the operating system with a zillion threads. We can just slow down an individual process. So while forking a child process is currently allowed, we still have the system calls in our operating systems. We would use that sparingly when it made sense. Okay? And one of the things we're going to talk about here is in some operating systems, it will make sense more often than other operating systems. Because some operating systems will schedule threads on multiple CPUs. So even though the thread is owned by the parent process, the thread passes through in some way to the operating system and then is allowed to be scheduled on multiple processors as fill-ins, right? Because we'd like to keep our CPU busy 100% of the time. Well, now we have 4 CPUs in a quad-core situation that we need to keep busy 100% of the time. And if you listen to Intel, they say they have the hyper-threading thing. So technically, you have 8 logical cores that you need to keep busy 100% of the time. I think I mentioned that at some point, that they call it logical cores, but it's actually a thing called pipelining, where it's in a... You can't really do 2 things at once. You can just kind of save yourself a little bit of time during the transition, but whatever. But the punchline is that if in a single core CPU scenario, I've mentioned that maybe the CPU sits idle 90-some% of the time. Often, CPU's usually idle. Would we say that in a quad-core situation, now we have 4 CPUs that are going to sit idle a large percentage of the time? So it's even worse. Okay, and this was actually exemplified by Apple in the early days. So yeah, it's hilarious to look back. Look how Apple is perceived today, and look back at some of the things they did in the past, which were just completely ridiculous. But people still bought into it. We've seen the Apple fanboys for years and years and years just drinking the Kool-Aid. It's so funny. There was a commercial years ago when this was still when Apple was running the PowerPC processors. So they had the G4 processor. Okay, so the PowerPC G4 processor, which was the last PowerPC processor that IBM made them, but that Apple had. And so the idea was that at the time they sold Mac Pros, so not a MacBook Pro, but a Mac Pro with a G4 processor in it. And then they made an announcement at, I don't know if it was Macworld or whatever back then. And the announcement was that tomorrow, for the same price as our current single processor Mac Pros with it was like a 1.4 gigahertz G4, let's say, you can now get a machine with two. It wasn't a dual core. It was 2 separate processors. So a dual processor G4 for the same price. 2 brains is better than 1, right? And Apple, the commercial, it was like it had a tank. Okay, the tank commercial, and it's 2 heads is better than 1, and the G4 was the dual core, dual processor G4 was the first consumer supercomputer that can do more than a teraflop of computations. That's a billion computations per second. That's what it translates into. It just sounds cooler when you say teraflop, right? What the heck's a flop? But it sounds awesome. All right, but punchline. So Apple had these commercials, and so wouldn't you say? So Apple's always been, the marketing genius type people, right? So wouldn't you say that would excite you if you were already drinking the Apple Kool-Aid and you had a Mac Pro, that you would look at that commercial and say, oh my gosh, supercomputer in my office. You run out and you give Apple your cash. You just want to know where to give it to them, right? How do I give you my cash and get this new piece of technology? Now the funny thing was, anybody know the backstory with this? A little bit of an interesting punchline with this machine. This was back when it was still running Mac OS 9. So before OS X, which was based on Unix. Now, a little bit of a problem with OS 9 was that it didn't support multiple processors. So they sold you a machine with a second processor in it, preloaded with an operating system that didn't support it. There was a few applications, Photoshop was one of them, that sorta kinda took advantage of that second processor. They wrote their own code to kind of light it up and get the guy kind of rolling down the street a little bit to do some side-loaded stuff for them. And then on top of that, we'll talk about multitasking in here, but we mentioned that Apple also had preemptive multitasking back then. So it wasn't even good multitasking. It was like fakesy multitasking. All right, so you had bad multitasking, 2 processors on an operating system that didn't support more than 1 that Apple was selling, and it was just flying off the shelves like hotcakes. Because it was Apple. And Apple made something new, and it must be good, right? It's the thing. So kind of an interesting backstory there. But getting back to what we were talking about was this idea that if our CPU scheduler's goal is to keep the CPU as busy as possible, as close to 100% of the time as possible, we want to have as many resources as we can pull from to keep it busy. That could be PCBs, so processors that are ready to run. So we already talked about having these multiple queues of priority for those guys, right? So we have the highest priority guys, we'll feed off that. Then we have a little bit lower priority, a little bit lower priority. Then we have the steerage. It's like, look, we don't really care if you get to these, but if you have a chance, throw it onto the CPU and let it cook a little bit. It's kind of like when you go to one of those cookouts and you see the burgers, the hot dogs that have been there for a long time and they just kind of keep throwing them back on the grill to just keep them warm. It's that, but on a CPU. So in any case, now wouldn't it be cool if we also allowed it to schedule threads? Let's somehow let you throw a thread onto our processor that's not busy. So by default, threads are really sharing the parent CPU time, right? But from a user's perspective, if the goal of the operating system as a whole is to fake out the end user, wouldn't it be nice if the CPU is sitting there literally doing nothing for us to go ahead and just kind of toss a thread over there and let him cook for a little bit, even though the parent might be getting CPU time on another processor? Okay, so fine, this process is technically getting extra CPU time, but only because we had an open resource. Okay, not because he's being treated with special attention or something like that. Does that make sense? We might as well use the processor if it's there. Okay, so we have to start thinking about what is it going to take in order to implement that model, because by definition, threads are managed by their parent process. Startup disk is almost full. Give me a moment. Sometimes I forget to close QuickTime. All right, back in business. All right, so because threads are actually managed by the parent process, we have to be careful about how that management actually, how do we allow threads to leak out of a process and actually be able to be scheduled by the CPU scheduler. Make sense? So it's almost like we're undoing some of the benefits of a process, but we're undoing of a thread, but we're undoing it kind of in a controlled way. All right. So whatever. Well, this is talking about a multi-threaded server architecture. It's actually kind of interesting. So think about before we had threads. If we had a server we were logging into and 10 people wanted to log into a server at the same time, they would literally have to be dealt with synchronously. Person 1 logs in, then person 2 gets to log in, then person 3 gets to log in. You have to wait in line to log in. Well, how long does it take to log in? Any of you ever forgotten your password for a site? So logging in takes anywhere from 5 seconds up to 3 days. Okay. Takes some time, right? So logging in isn't necessarily fast. So that would be bad. So now what we're going to do is we're going to spawn off threads to handle authentication for multiple users. So we have the one server that's sitting there just waiting for the phone to ring, waiting for somebody to establish a socket connection to the server. When the phone rings, they pick it up, they spawn off a thread, they hand the open socket to that thread, then they hang up the phone, waiting for it to ring again. So that would be an asynchronous approach to authentication. Every single time a new person tries to log in, the process spawns a worker bee to go and handle that authentication. Now, we might decide, okay, well, we're going to deal with some sort of maximum number of users at one time. We did talk about that threads in general. We can still think about this in general terms. A thread shares the CPU time of its parent. Okay, so we don't want a parent to spawn off so many threads that it basically starves itself out. right? It's like, okay, well, I have 4 billion children, so we're each getting, you know, a quarter of a nanosecond on the CPU, and then we have context switching. So, but it's not really context switching. It's like halvesy thread-based context switching, but it's still bad. All right. All of a sudden, you have a process that can't accomplish anything because it has too many children running around. Pretty much like real life, right? You know, if you have a family that has 2 kids, no big deal. You got a family that has 200 kids, it's a problem. Okay, like what Octomom? Can't she like? You know who I'm talking about?
Yeah, I'm curious where it's going.
Well, I'm not talking about the recent stuff. I'm talking about just the fact that she has 8 kids.
She can spawn a lot of children.
Yeah, she can spawn. She did spawn many children, and therefore she has you know, a lot of responsibility at home with a lot of things. So probably isn't acting very efficiently, right? There's probably situations where she yells at a kid and it's the wrong name, that kind of stuff. You know, that's why you just index them. Don't use their name. It's bucket 3. Or put little Post-its on their head. So it's basically a pointer. You, number 4. Bath time. All right, so I was pointing at you, Dirty Randy. All right, so in any case, this is the multi-threaded server model. So this solves a lot of problems for us, but what we might do is might limit the number of threads that will spawn off. So we won't allow 1 million people to authenticate simultaneously, but maybe we'll handle 10. Does that help solve the problem? You know, we don't know how long it's going to take somebody to log in, but realistically, are 10 people going to take 3 days? Probably not. Maybe, you know, 10 can go up to 30 or 40, whatever. You know, we can play with that number, but the punchline is that we wouldn't necessarily allow an infinite number of threads. So in those situations, what we'd often do is we'd create something called a thread pool. Because spawning off a thread, so going back to the example we had where somebody establishes a socket connection to that phone, I lift it up, then I poof, spawn off a thread, Harry Potter style. You know, is it do you do it? Does the wand flick thing have anything to do with it, or is it just the words?
90% of it.
Oh, it's not the words. The words
There's
are.
a select few wizards who can do wandless magic. It's supposed to be super powerful.
See, but this guy can.
Wow.
Okay, no wand. It's not built into the thread model, at least not in Unix. So in any case, new thread is born. We hand it off. Now, are threads born instantaneously if you were guessing? Or is there probably at least some sort of delay? It might be in nanoseconds or microseconds or something like that, but they don't just happen, right? Okay, so there is a time associated, a cost associated with spawning off a thread. So we could, so if we think about this from a server architecture model, would you as a user prefer that the server you're going to talk to take more time to launch initially, the one time it started, 3 weeks ago or whatever? Or would you prefer that every single time somebody talks to it, it's a little bit slower than it would be otherwise? Is it okay for a program to take 30 seconds to load if after it's loaded, it's faster than it would be if it took 3 seconds to load and then it's slower once it's loaded? That would be better, right? So that's where thread pools come in. So what they essentially do is they pre-spawn the threads at the beginning of the, when the server is born. So now we kind of have a stable of threads. So whenever a new socket is created, rather than spawning off a new thread, we would just grab the next available thread, hand it off, and say, go and do your job. Get back in the stable when you're done. That make sense?
Is that the server creating them, and is it like a random amount, or is it like they know the program's coming in? They're like,
well, the server would. At some point, you're going to have to give some definition of what the server does, right? So if this is an authentication server, it wouldn't be a random number. It would probably be we will allow a maximum of 20 people to authenticate at once. Okay, so this is no different than if winter's coming, right? So if you had a snowplow business, how many snowplows do you have in your stable of snowplows to manage the number of customers that you have? All right, you probably don't have one snowplow per customer, but you probably have, one snowplow for every 10 customers, something like that.
The book mentioned that the pool changed dynamically depending on how many, like, the load on the server.
Could be, yeah. I mean,
Figure that out.
depends on, well, I mean, so that's just servers acting, intelligently. If a server is noticing, so maybe a server has a threshold. So a connection comes in and it picks it up and it says, okay, it reaches for the stable and realizes the stable's empty. All right, so then maybe what the server does is this, that, well, at that point in time, the server gets to decide, am I going to service this person or am I going to tell them to wait? Okay, put them on hold, like if you call the doctor's office or something, okay? All right, so, but do I put them on hold or do I just go ahead and spend a little extra time right now building a thread to allow them to do, and then maybe do I dynamically create a couple of more threads to fill up the stable? So based on statistics of how the server is being used, you modify the number of threads in your stable to kind of support that load. So as more and more people are hitting it, you're going to be spawning off more threads in your stable, and now all of a sudden you have additional threads in your stable. So even if this guy is coming in, so let's say we have, let's use an example. Well, I mean, this is actually a real life example. Typically, when a new game comes out, an online game, what's the first part that breaks? The login servers, right? Okay, people start having trouble getting into the game. Okay, once they're in the game, maybe things are okay, but they can't even get into the game because they can't get past the login servers. So if and other games have done this, I see this with World of Warcraft. World of Warcraft, in its heyday, would have zillions of people trying to connect at once, right? Okay? And then what did they do? They started instituting queues. So they said, well, we're only going to allow this many people to log in at once, and then they also had a queue for how many people they'd allow onto a server at once in its real heyday. Well, they were dynamically creating more and more servers. Okay, well, not dynamically, but they would introduce more servers into their available servers for people to go into. But when a brand new game comes out that requires authentication, when you have a huge influx of people, significantly more people than they ever tested with, right? Beta testing, even in a public beta, maybe had, let's just make up a number. Let's say 1,000 beta testers, something like that. Now the game hits the shelves, and now you have 100,000 people, 500,000 people, whatever it is, a lot more people trying to hit the login server at the same time. Okay, this thing was never stress tested under that condition, right? So now all of a sudden that's where the thing starts breaking. Well, if they build in some dynamic pooling into that, now all of a sudden as the number of communication things or the number of login attempts start going up and we don't have enough threads in the pool to manage it, well, then we have to start spawning new threads to manage it. Okay, well, now what happens? So now we have, instead of 20 threads in the pool, now we have 200 threads in the pool. Okay, because that's the number of, if the authentication takes, 5 seconds on average. Let's just say that's the number. If each one of these guys is going to be busy for 5 seconds, then come back and get into the pool, hopefully 200 is enough to manage all the people we might have within a 5-second period. Maybe that's true, maybe it's not, depending on the game, but that's the guess. But at some point, we overwhelm that process with multiple threads. That makes sense? That's when they have to start buffering on the thread pool. So now we're going to throw people in line for the thread pool. And that's its own thread, right? So now we have another thread just for managing the thread pool. Get in line to get on the merry-go-round. Those things still exist, merry-go-rounds? Do they? It seems like a really ridiculous name for something, merry-go-round.
Pretty straightforward.
Yeah, but what's fun about that?
It's merry. You go round. That's
Go-
what else you need.
It's not fun.
I think the idea is.
Yeah, when you were 2, it was fun.
Yeah, it's not meant for you.
I got yelled at the other day in Meyer.
Where is this?
So I was checking out, and they have one of those mechanical horsies. It costs a penny. Costs a penny. But they had, next to the thing, they had a dish of pennies. Like free pennies. So even though the thing took a penny to start. So my wife was still checking out, so I figured I'd go ride the horsey. So I was too big for the horsey. It seemed to be going just fine. Like, it didn't seem to have any trouble at all. You know, there's not that many, but it's probably just steel pipes, right? Just I was having a good time. And the guy who's in charge of the handicap carts came over and told me to get off.
That's not your jurisdiction.
Go back over to your handicap buggies. I also was riding a handicap buggy. Those are a blast. That's the best way to go around Meyer, is in a handicap buggy.
I thought you only needed that for your knee.
Yeah, my knee, it's mostly, actually, it's completely better, but you can never be too careful.
Why don't you just drive your
The hoverboard?
The hoverboard to good use.
I should do that, but that doesn't have a horn.
The brake one.
Carry one of the bike horns with you.
Doot, doot.
Don't bring your own. Go get one from the store.
every time I go into the store, the very first thing I do is I make a beeline for the for the dog squeak toys.
There's got to be an app for it.
It could be.
Wouldn't it be funny if you're like a dog squeak toy or the bike style?
I know exactly where the squeak toys are too. They're back by the fish.
Just get one.
I could also carry on one of the beta fish. I haven't, People actually tend to leave you alone because they just assume you're special. Why is that a problem? My wife says I'm special. It actually happens way too often when I'm in stores that my wife starts separating herself from me to pretend like she doesn't know me. Because I make dinosaur sounds and stuff like that in the store.
I think we should try to get some store video of that horse you're riding.
I'll do it again. No big deal. Okay, so let's keep trucking here. So here's an example of a single core machine, how it would handle multiple processes, multiple threads. We can think about those guys as being synonymous right now. Okay, and notice it just handles them in the same order, gives this guy some time, this guy some time, this guy some time, this guy some time, then goes back to the beginning over and over and over again, and this assumes they all have the same priority. Multi-core system, somehow it's going to stagger them, right? So notice that T1, T3, T1, T3, T1, T3, so on and so forth. The other two guys are on here, so you've doubled the speed, potentially, as long as we can keep it busy. All right, so now we're going to start making this difference between user threads and kernel threads. Okay, and this is the mechanism by which we could choose to schedule threads on the CPU. All right, this is how this is going to happen. So we have 3 different standard libraries that we're going to consider in here. There's more than just these 3, but these are our popular ones. So we have the Unix standard libraries for threads, which is the POSIX standard, and those guys are called pthreads. That's the type of threads it's called. Then we have Win32 threads. That's the Windows threads. And then we have the Java threads. So they're pretending like Java is an operating system. It's a virtual machine. Let's just say it's fine. All right, so those are our Java threads. Those are the 3 different libraries the book considers. Then we have a second kind of thread. So we have user threads, which are these guys. And those are specifically associated with user level programs. Then we have kernel threads, which are associated with the operating system itself. All right, so these are supported specifically by the kernel, and we have examples of every kernel basically supports kernel threads in some manner, but it's not all created equal. So we have a multi-threaded model, and this is how user threads connect to kernel threads. So we can have a many-to-one model where many user threads are connected to a single kernel thread. All right, so in that model, what would happen? If I have 10 user threads, so 10 threads spawned off by, could be 1 user program, could be 5 user programs, and they all get kind of linked up to one manager, if you will, okay, which would be a kernel thread. And now that kernel thread could get scheduled by the CPU scheduler. Okay, well, he would get scheduled by the process scheduler in like a new queue called like the thread queue or something like that, and then he would be in line for available CPU resources by the CPU scheduler, the short-term scheduler. Okay? But instead of every individual user thread being potentially schedulable on an individual basis, the kernel thread that's in charge of them would get CPU time, and then he would split his CPU time among the threads in whatever way he decides, among the threads that he's in control of. Kind of make sense? As opposed to a one-to-one relationship where every single user thread is associated with exactly one kernel thread, and kernel threads can be scheduled, so this is going to give us the most flexibility, where at this point, user threads are then treated basically identically to processes. They just weigh less. And then we have a many-to-many relationship where every user thread is associated with potentially several kernel threads, and vice versa, right? Every kernel thread then has many user threads under its purview. And maybe this increases the potential that a thread gets CPU time, since kernel threads are scheduled by the CPU scheduler somehow, right? And we might have 5 different kernel threads that all link back to the same user thread, so now there's a higher probability that that one user thread's going to get some CPU time.
So do kernel threads always get CPU time then?
They would be a relatively low priority, but yes, I mean they're always in line for CPU time, assuming the operating system supports it.
Okay.
But they wouldn't be a highest priority type thing. Yeah.
Depending on how schedulers are implemented, do some have like separate schedulers for kernel threads and then like schedulers for like user threads?
Oh, absolutely. Well, you would never have a scheduler for a user thread. Never escapes the user program, so it never gets down to the kernel level.
Like it's always in the program.
It by definition it is. Yeah, user threads are always self-contained. They never leak out. Okay, they basically are handed walkie-talkies that connect them to one of the kernel threads at the system. So I mean, these guys are basically similar. Just kernel threads are allowed. They have security access. Right? They're allowed to be near the kernel, near the CPU, stuff like that. Where our is this one of the new Starbucks cups? Oh, so isn't that the new thing? How did I jump onto that? Yeah, isn't that the new thing that the Christians are complaining about? Christian worldview.
Like one person said something, and then the news was like, "Oh my God, everybody's freaking
That
out!"
they took away the Christmas symbols on there.
But they never even had Christmas symbols. It was just like snowflakes or something, and then they were like,
Close enough for Christians.
apparently.
Christian worldview.
And they took those off, so now they're trying to kill Christmas.
Pretty sure all the news stories are about the Christians who are complaining about it.
Yeah.
Yeah, I don't really understand. Like, how is
I haven't heard it.
snowflake synonymous with Christianity? Like,
Well, it's more synonymous than just red, but technically you can say, well, red, that's the blood of Jesus. It's basically like you're taking coffee-based communion if you kind of take your glasses off and pretend like it's a pastor giving it to you, and you don't break any of those other rules. Huh?
Just gotta eat those scones.
Yeah. I'm here for, Starbucks communion. I'll take a small red coffee cup and a scone. And we'll just let the Lutherans, it's the blood and body of Christ. It starts off as it is bread, it is wine, but then it's in, within, and beneath or something like that.
In with and under.
Yeah, in, with, and under. It becomes it. So we'll just kind of rely on God to kind of step in and turn our small coffee and the scone into what it needs to be. Fast food communion. What's up? Well, I think Christians just make the leap. Like snowflakes equal Christmas, forget about Santa, this is the Jesus thing. Right. Right, but we're not going over there, it's scary. All right, so definitely a bunch of Christian worldviews in there. Check mark, check mark, check mark, asterisk. All right, so here's our different multi-threading models. But to answer you actually asked the question. the punchline is that only kernel level threads have access to the CPU. So if a user level thread wants there to even be a fighting chance of it getting CPU time as an individual rather than as part of its parent's CPU time, it has to link in one way to a kernel thread. It never actually gets to leave a process. That make sense? So that's kind of the scoop there. So we have 3 different ways of handling this. All right, so, and here's examples of implementations of these. We already said what a many-to-one is. Solaris green threads and GNU portable threads. Anybody know what GNU stands for? It's an interesting acronym. It came kind of from Linux. It's a Linux. Huh?
The G is no, right?
I'll give you a hint. The G is GNU. GNU is not Unix. That's what it stands for. So GNU is not Unix.
It's like why?
Yeah, it's funny.
So would it be a decent statement to say that each user thread needs to be attached to at least one kernel thread?
If it intends to be independently scheduled on the CPU.
Okay.
Yeah, it's not a requirement. It's just a reality of modern operating systems. Because they have that goal of maximizing CPU usage, they want to have the ability to leverage threads that would like CPU time that might not be getting CPU time if we have an open seat on the CPU. Make sense? All right, so there's some many-to-one things. So Solaris, dead, GNU portable threads. These are the P threads that we mentioned before. That's what the portable thread stands for. So this would be the Linux model of things where lots of user threads are associated with a single kernel thread. Okay, so we allow them to leak outside of their user process. So now they basically have 2 different ways of getting CPU time. They can either share in the CPU time of their parent process, or they can get some CPU time as handed to them by the kernel process that's in charge, the kernel thread that they're associated with. All right, then, so this is the many-to-one model, and those look creepy. So let's go on. So one-to-one. So Windows NT, Linux not using pthreads. So GNU portable threads are, that's one implementation of threads in Linux. Linux in general uses a one-to-one thread through the Linux thread library, not the pthread library, which then gives the maximum, well, actually this is probably the middleman based on the 3 models we gave. This gives an improved chance of a thread getting independently scheduled because we're going to associate every user thread with exactly one kernel thread, and then we're going to somehow work kernel threads into the CPU scheduler. Okay, so Windows NT, XP, 2000, Windows 7, Windows 10, all Windows. Windows uses this guy. Linux uses this guy, and we say modern Solaris, but Solaris until its death. We'll just say that. Is the one-to-one model. It's actually kind of even creepier. So then we have the many-to-many model here. We talked about that already. So early versions of Solaris, and then the server class operating system. So remember a while ago we talked about how there are differences between the server operating systems from Windows and the consumer operating systems from Windows. So in the server operating systems, NT, 2000, then since then it's all the server whatever, they have something called the thread fiber package. Because in a situation like this, when you're a server, you care less about an individual user and more about maximizing the performance of the server for multiple users. So that's when kind of hedging our bet against threads getting CPU time, if at all possible, comes into play. So that's where we'll associate every user thread with potentially multiple kernel threads. So they have a higher percent chance of getting some CPU time if the CPU is available, because all of these are going to still operate under this idea that that threads are scheduled on the CPU as second-class citizens to processes. They don't have to be that way. That's just typically how the operating system is written. Processes are important. Threads are the afterthought. But if nothing's using the CPU, let's go ahead and get a thread on there. Make sense? So that's the many-to-many model. All right, so 2-level model, nobody uses this. These are all dead operating systems. So this allows user threads to be bound to kernel threads. So they don't have to, in the other models, they get to kind of be, they can be jumped around. They can be rescheduled, reassigned to other managers, where the 2-level model allows them to literally be locked into a kernel thread. Pretend like it doesn't exist. I'll never ask you about it. So thread libraries, these provide a programmer with the API for creating and managing threads. So in Java we have an API for generating threads, and in Windows we have the same thing, and with Linux we also have the same thing. So there's two different ways of implementing this. We can have a library that lives entirely in user space, which means that the threads you're working with are always user threads, and therefore they would get linked up to a corresponding kernel thread based on however that operating system is implemented, versus a kernel level library that's directly supported by the OS, where the programmer might have some flexibility for determining the type of threads they want to create. All right, so now you might have a situation where instead of creating a user level thread that can only do user level stuff, we might want to create a kernel thread. Maybe we have to have something that's going to make a lot of system calls. And if we're making system calls from a user level thread, we have to go through the bouncer. Okay, there's a delay. Okay, if I'm a user level thread or a user level program and I want to make system calls, I have to ask for permission to talk to the kernel, right? But if I'm a kernel level thread, I'm already working in headquarters. All right, I'm already below the level of the bouncer. I'm in the building. So now I can make those system calls, not necessarily without checking, because some system calls are more protected than others, but certainly there's at least one less layer of checking with kernel level threads for system calls. All right, so some libraries allow us to directly access this. Other libraries, so they sometimes give us the little free pass card, so that our threads don't have to talk to the bouncer. Other ones make you always go through the bouncer. All right, so here's this implementation of pthreads. So it may be provided either as user level or kernel level, so they support both thread libraries. Situationally, when you compile Linux, you can choose the options for how pthreads work in that version of Linux. Distributions of Linux that have pre-compiled the kernel will vary. So I think probably Red Hat will allow kernel level, where Fedora, which is their consumer product, will not. Consumer product probably needs to focus on the user level threads. The server product, the one that's meant to be a server class machine, more than likely the applications running on it are going to be doing system calls. Therefore, let's go ahead and streamline that, not have to have them talking to the bouncer very often. Go ahead.
So if I'm sitting and I have two computers, one doing like each of the different things, would I be able to notice a difference between them, or would they be?
If you were the only user on both of them, no. If you had multiple users on both of them, possibly.
Okay.
Yeah, because it's going to perform, it's going to scale differently as you have more users hitting the system. But one-to-one won't make a difference. Yeah, one-to-one, if you're on, a Windows Server class machine versus a Windows consumer class machine, your biggest difference you're going to notice is driver support. That's it. So how good your graphics card works or something like that, depending on how that, because drivers are almost always written with the consumer operating system in mind. So if some aspect of the driver is implemented differently, is implemented in one way, and the server operating system implements that part of it differently, you might notice performance differences. Okay, so this guy is a POSIX standard. So earlier I mentioned it's POSIX pthread. So POSIX is a standard that's under the IEEE thing. This is its secret code number. So things that follow the POSIX protocol, the POSIX interface, the POSIX standard, these are all synonyms for each other, need to meet whatever this guy says it is. All right, and this is a API specifically for thread creation and synchronization, and we've been talking about that with inter-process communication, and we'll swing back on it here in the next chapter, I think. So API specifies behavior of the thread library. Implementation is up to development of the library. And this is an open source project, pthreads. So this is part of the Linux design thing. So common in Unix operating systems, Solaris, Linux, Mac OS X, because Mac OS X was actually OpenBSD with a Mac front end on it. So there's your evidence there. Solaris, let's just call that dead. So really, Linux is going to be your real cool kid. Mac OS X is going to be your cool kid in a dress. It's the punchline. All right, questions about any of that stuff? So we'll look at a pthread example at the beginning next time. No assignment today, but we'll probably have another one on Monday, but it depends how far we get. Sound good? All right, have a good weekend.